Hello everyone, hope you are doing well. Finally, we arrived at the last lecture of Chapter 9, the best hydraulic section. In today's lecture, I'm gonna talk about the best hydraulic triangular cross sections. As you see here, we have a triangle that has two sides of equal lengths. The angle of apex is assumed to be alpha, and the water depth is assumed to be y. And our goal is to find the most efficient triangular cross-section. As previous lectures, in order to find the most efficient section, we need to calculate wetted perimeter and minimize it. Okay, let's first talk about the geometrical characteristics of this triangle. Side slope is given here. The side slope 1 is 2x. It means that 1 meter vertical makes x meter horizontal. Therefore, if the water depth is y, or the vertical is y, the horizontal should be xy. And we can say that half of the top width equals to xy in this triangle. Therefore, the entire top width is 2xy or 2yx. So I know my top width, which is the base of this triangle, and the height is equals to y. Therefore, I can calculate area. Yes, area equals to height times base divided by 2. Y times 2yx divided by 2 gives you xy squared. The area or surface area equals to xy squared. How about the wetted perimeter? Wetted perimeter is the length of these two sides. Yes. Using Pythagorean theorem, we can calculate length of each side. Therefore, if the height is y and this side or the base is yx, therefore the hypotenuse would be square root of yx square root of y square plus yx square. Or you can say this side equals to y square root of 1 plus x square. We have two sides, therefore we multiply one side by 2, which gives us wetted perimeter as you see here. Now we have wetted perimeter and we can start differentiation part of our work. You see here in this equation I have two variables, y and x. And if you remember in previous sessions, when we had a second variable like b, bottom within rectangular cross section, or x as what we had in trapezoidal cross section, we replace one of the variables with the other variable which is known. Which variable was known? If you remember from the beginning of these lectures, we assume that area is known, A is known, and in other words, we solve the problem for a given area. Therefore, we can replace either x or y with the function which has the term area. At the first, you see that I differentiate the wetted perimeter with respect to x. Therefore, it means that I replace the value of y with its corresponding equation in terms of a. From here, I can say that y squared equals to a over x, Therefore, y equals root a over x. If I replace this y with this value of y, I will have weighted perimeter equals to 2 square root of a over x multiplied by this root. After simplification, the final weighted parameter equals to this equation. P equals to 2 times square root of a root of x plus 1 over x. Now I have to take derivative of this equation with respect to the x. You see that I have a constant term 2 square root of a and a root function which I must carefully take the differentiate of this function. Therefore, I assume this is my constant to take a derivative of this function. Like usual, I can assume x plus 1 over x equals to u. Therefore, the derivative of the square root of u equals to u prime over 2 square root of u. Yes, the differentiation of u equals to differentiation of x, which is 1, plus differentiation of 1 over x, which would be minus 1 over x squared. Then our denominator would be the square root of u, again the square root of the same function, multiplied by 2 at the denominator. However, from here I have a constant 2, therefore they can cancel off. And the final differentiation is like this equation, dp over dx equals to this. To get minimize p, it should be 0. Therefore, here the numerator should be 0, which means that 1 minus 1 over x squared equals to 0. And this equation means nothing that x equals to 1. Therefore, here my x value is 1, and I can say that the side slope is 1 to 1. Therefore, uh, the theta, this theta should be 45 degree because those both perpendicular and base are constant. The other conclusion is this theta is 45 degree. I will talk about these angles and their relationship with alpha a bit later in this slide. Yes, you see that I found this theta equals to 45 degree. Therefore, this is 45 also. It means that this angle is also 45. And therefore, for the inner angle of this triangular, the alpha should be 90 degree. Therefore, this is a right triangle. And we can say that this means that the section is half of an square or half square. Okay, here I would like to solve the problem of best hydraulic triangular section in another way also. Here you saw that we replace the value, the term y with its corresponding value from the area equation. In the second way, I would like to replace the x and take the derivative of the weighted perimeter with respect to the y in this example. So, as previous, we know that area is xy squared. Therefore, from here, x will be a over y squared. And from the beginning, I know that weighted perimeter equals to 2y times square root of 1 plus x squared. If I replace the value of x here with this, what I will have p equals to 2y times a square root of 1 plus a squared over y power 4. Now I have to take the differentiation of the weighted parameter with respect to the y. To do differentiate, 2 will be taken out. The answer is here, 2 will be taken out. Because we have no relation with 2, it is a constant. Now y is the first function, and a square root of 1 plus a square over y to the power 4 is the second function. To differentiate, the first function must be multiplied by the differentiation of the second function and plus the second function times differentiation of the first function. Again, here you see that I multiplied y by the differentiation of second function. This is second function. And here I have a function in terms of y, which is the multiplicative term, and differentiation of this square root of 1 plus a square over y square can be solved similarly as I talked about the differentiation of a square root of u, which is equal to u prime over 2u. Therefore, differentiation of u here would be 1 plus a square over if u is 1 plus a square over y square, u prime will be 0 plus a square differentiation of 1 over y to the power of 4, and therefore u prime will be a square times minus 4 over y to the power of 5. As now I know I calculated u prime, I have to divide it by 2 square root of u. Therefore, as you see here, I divided u prime with 2 square root of u, which see here. This is the multiplication of first function to the derivative of the second function. Now I have to add the result with the differentiation of the first function multiplied to the second function. Differentiation of y with respect to the y is 1, and differentiation of the which must be only multiplied by the second function. Therefore, this is my differentiation of weighted parameter with respect to the y, but I simplified it. As you see here, I can cancel out y with y from here. Therefore, I will have y to the power of 4, and also these two can be cancelled with the half of 4. The result is given here. You see that the first bracket will be equal to minus 2a square over y to the power of 4 times square root of 1 plus a to the a square over y to the power of 4 plus the second bracket, which is only 1 plus a square y square. Therefore, to get a minimum weighted parameter, this function equation should be equal to 0, and therefore I can transfer this negative sign term to the next to the right hand side, or you see that I can say that 2a squared over y to the power 4 times square root of 1 plus a squared over y to the power 4 equals to root 1 plus a squared over y to the power 4. And from here, I can, you see, I can get this conclusion: 2a squared equals to y squared multiplied by 1 plus a squared over y squared. Let's check again where was what I did to get that equation. Only I multiplied the denominator to the right hand side. Therefore, I can remove this root sign, and what I have, I will have 2a squared equals to y to the power 4 times, in parentheses, 1 plus a squared over y to the power 4. Yes, as you see here. Now I can multiply this y to the power 4 to the parameters of within the parenthesis. Therefore, I will have 2a squared equal to y to the power 4 plus a to the power 2, because it will be cancelled from those sides. Then I can transfer this a squared to the left hand side, and I can find this conclusion: a squared equals to y to the power 4. Take a root of both sides, gives us a equals to y squared. From the beginning, we assume that A, or the surface area of triangle cross section, is also equal to xy squared. And in the case of the most efficient triangular section, we see that A equals to y squared. These two equations imply that x equals to 1, and this is the same conclusion that we had from the previous method. So let's see our triangle cross section again with x equals to 1. Therefore, if the side slope is 1 to 1, therefore for the y, half of the top width equals to y also. And from here, we can see that this triangle has the identical side. Therefore, it is an isosceles, and the theta here, or angle here, is 45 degree. So if it is 45 degree, we can calculate top width, and also we can calculate length of the side. Top width equals to 2 times of y, because if it is 45, this side is also 45, and therefore this length is equal to this length, and for the depth of y, the top width equals to 2y. And the length, as we know that the length equals to y square root of 1 plus x squared. We already derived this equation using Pythagorean theorem, and here x equals to 1. Therefore, this length should be y square root of 2. Therefore, I can calculate weighted parameter as a summation of this length and this length, which is 2 times of y times 1 plus x squared, and this is 1. Therefore, weighted parameter equals 2y square root of 2. And using this equation, or this equation, I can calculate surface area equals to y squared. Okay, I already know that surface area equals to y squared, and if one asks you what is the hydraulic depth, what is the hydraulic radius for the most efficient triangular section, you need only to divide A by weighted parameter, which here you see y squared divided by 2y square root of 2, which gives you y over 2 square root of 2. You know that in triangle or trapezoidal sections, hydraulic radius was equal to the half of the depth of water. However, you see that in triangle section, hydraulic radius is too much less than hydraulic radius of the trapezoidal or rectangular section. By this, we know that the best triangular cross section is a right triangle with the hydraulic radius equals to the y, or equals to the half of equals to the depth divided by 2 square root of 2. Okay, let's see an example and see how we can use the information we learned in this lecture. As you see, question says that a triangular irrigation lined canal carries a discharge of 25 cubic meter per second at bed slope equals to 1 over 6,000. If the side slope of the canal are 1, 1 or R1:1 and Manning coefficient is 0.018, the central depth of flow is equal to which of these alternatives? Here, to solve this equation, you see that the problem gave us the Manning coefficient as to 0.018. Therefore, we can use Manning equation to solve the problem. This is multiplication of area to the velocity, and the Q is given as 25, as you see here. And what is the area in triangle, the best triangle? You might ask, from where I know this is the best triangular cross section? From here, you see side slope is 1 to 1. Therefore, I can replace area with y square, as I already got this. And I can replace the hydraulic radius with the y over 2 square root of 2. Then I can solve this equation because S0 and N is non-variables. As you see here, I changed 1 over 6,000 with 0.013. Therefore, y to the power of 2 times y to the power of 2/3, which equals to y to the power of 8/3, will be equal to 25 times this value times this value to the power of 2/3 divided by the 0.13. And from here you can find y to the power of 8/3, and finally you can get the value of y, or depth of the flow in this triangular section, equal to 4.91, as you see here. Okay, this is all the materials for this lecture, and by this session I think that we studied full chapter 9, and I would like to request you to go to the textbook and see and solve those examples available in your textbook. Again, for the case of any question, please be in touch with me. Have a good day. Thank you. See you in next session.